Good day everyone, my name is Sabriansyah Akbar. I'm from Department of Materials and Informatics, Interdisciplinary Graduate School of Agriculture and Engineering, together with my supervisor, Professor Ichijo Hodaka from Department of Environmental Robotics, Faculty of Engineering. We are from University of Miyazaki, Japan. Today we are going to present our paper with the title of the optimizations of dual receiver wireless power transfers. Start by the introductions. Triggered by the growth markup in electronic appliances require the needs of charging multiple devices at once. And in the wireless power transfer field, in order to obtain high power, research considers some fields as a research hotspots, such as an architecture field and optimization field. And some methods are used to obtain high power in wireless power transfers, such as using the impedance matching and using the idea of resonance and then optimization technique. The next is we want to explain the problems that we want to solve in this research. Start by the common wireless power transfer circuit here as the figure 2. And while we propose the wireless power transfer circuit as in figure 3. As we see, the difference between both pictures here is the number of the capacitor, while the common wireless power transfer circuit are using the capacitor on each side of the circuit, while in our proposed circuit here, we are only using one capacitor. Therefore, by using a single capacitor, we can reduce the complexity at the receiver side. Also, we can reduce the parasitic resistance owned by capacitor in the receiver side, so we can increase the power in the receiver. And the common wireless power transfer circuit, once again, here is using the capacitor on both sides in the primary and each of the receiver side. And therefore, to obtain higher power, many research using the idea of resonance to obtain optimal capacitor and operating frequency by using this formula. Therefore, by pairing the capacitor with the inductance in the each circuit by using this formula, we can obtain high power in common wireless power transfer circuit. However, if we look our circuit here, our circuit cannot use the idea of resonance since our circuit only contains one capacitor, and therefore we propose an optimization approach to find the optimal capacitor value and the operating frequency to obtain high power without the idea of resonance. To obtain high power without using the idea of resonance, we propose an optimization approach, such as in the slide. Start with defining the system model. Then we conduct the optimizations, and then we will obtain the extending point of capacitor and frequency, so we can obtain high power for both receivers. Next, we want to explain how to obtain our proposed wireless power transfer circuit system model. And start from our proposed circuit here. We analyze the Kirchhoff current and voltage law. Then we define our input as the voltage of the voltage source, and then our output here, our output Y, as the voltage at load in the receiver, in the first receiver, and voltage at load in the second receiver. And then by defining our state space variables here as V1, I1, I2, and I3, we define the our matrix, state space matrix, as here. And then by using the state space equations, we can obtain our transfer functions for the load at the receiver 1 and the load at the receiver 2 um, noted by the GL1S and the GL2S. After we obtain the transfer functions of our system model, then we want to define our, before we conduct the optimizations, we want to define our problem set. First, by knowing that since our input here, the voltage of the voltage source is using the sinusoidal uh, voltage with U0 as the amplitude. And then, so our output here, our frequency response of the output here, displayed as YSS1 and YSS2, can be obtained in the equation 6. Therefore, since we are interested in the power in the load, in the first receiver load and the second receiver load, then we define the formula for the power as in the equation 7. Therefore, we for now we decide our power formula in the equation 7 as the um, objective functions f1 and f2 as in equation 8. Therefore, we can obtain our problem set as follow, where we want to maximize f1 and maximize f2 for the capacitor and omega, which omega here is represented as the frequency in radian per seconds. After we obtain the objective functions and the problem set, then we conduct the optimizations by using the numerical value as shown in the table, and then we substitute the objective functions with the value of each parameter shown in the table, and afterward we obtain that our objective functions as the equation 9. Therefore, we conducted the optimizations by using the problem set as mentioned below. Using the tools here, we are using Python and using the Python multi-objective optimizations module, and we choose the algorithm non-dominated sorting generating algorithm 2, since we have two objective functions here then that we want to be maximized. Then from the optimizations process, we obtain the capacitor value. It's at 21.4 nanofarad and the frequency as to around 243 kilohertz. Then we obtain the F1 equal F2 is at 0.12 watt. Here we have the same value for the F1 and F2, since the both parameter for the first and the second receiver as mentioned in the table is equal or same. The next scenario for the optimization is the second scenario, which in these conditions we make some values between the first and the second receiver is different. Therefore, we obtain a different objective function value where the first receiver objective function is at mentioned at the equation 11, and then the second receiver objective function is at the equation 12. Here, since we want to maximize both of the F1 and the F2, the result of the optimization was shown in the right figure, when the optimal solution is obtained when the capacitor is at the 18.5 nanofarad and the frequency is 252 kilohertz, where the power at the first receiver is obtained around 0.08 watt, and the power at the second receiver is 0.13 watt. Then from our first scenario of the optimizations, we want to compare our results, optimization results by the common and our proposed circuit with our optimizations approach, and compare with the common wireless power transfer circuit with using the resonance idea. Here, if we are using the common wireless power transfer circuit using the frequency idea, the resonant frequency idea at the equation 10, we obtain that the value of the first, second, and third capacitor from the circuit is 110 nanofarad, and the frequency will be at 102 kilohertz. Then we compare the result between the optimization in the first scenario and compare the result with the common wireless power transfer circuit with the idea of resonance. Using the LT-SPICE, we simulate both conditions. At the first conditions, where the optimizations give value for the capacitor at 21.4 nanofarad at the frequency at 243 kilohertz. We can see at the LT-SPICE simulation result at the left image, which is around 0.12 watt, both for the first and the second receiver. While in the using the idea of resonance using the common wireless power transfer circuit, it only able to obtain the power for the first and the second receiver at around 0.10 watt. Here we can show that our optimizations approach obtained a better power absorbed by the first and the second receiver. Then for the scenario 2, where the parameter value for the first and the second receiver is different, we want to show the optimization result obtained from the LT-SPICE simulations. Here in the second scenario, we obtain that the capacitor value is 18.5 nanofarad, and then we can see that the both first and second receiver is obtain maximum power at around 240 kilohertz. Therefore, we show that our optimizations result able to obtain the optimal solutions even when the conditions between the first and the second receiver is different. Then we can conclude that in the first scenario, our proposed circuit and extremum point of capacitor and frequencies obtained from our optimizations approach have better results than the common wireless power transfer circuit that use capacitor on the each receiver circuit and using ideas of resonant calculations. And in the second scenario, we conclude that our results show that our proposed model combined with the NSGA2 optimizations can obtain optimal results in the different situation of inductance coils, load, and mutual inductance. That's all from our presentations. Thank you for watching, and if you have any questions, you can send us an email or give some comment in the comment sections. Thank you very much, and see you next event.